Good evening, good day, and good morning to all of you. Welcome to the second day of the Löwdin lectures, or the Löwdin Symposium 2020. We're halfway through the symposium. Yesterday we listened to 8 very interesting presentations, and today we have another 8 of them. Again, the day is going to be subdivided into 3 2-hour sessions, altogether 3 sessions, and each session is going to contain 3 lectures, apart from the last session that will just be 2 presentations. Each presentation is 35 minutes plus 5 minutes for Q&As. For those of you who are attendees, I recommend you to use the Q&A option in Zoom and post your questions well before the presentation is finished. In between the sessions, we're going to have a 1-hour intermission. For the scheduling details, I recommend you to visit our website. And as I told you yesterday, today's schedule, there is a swap between the position of Martin Kwak and So Hirata. So with all of that said, I would like to welcome the speakers of the first session, which will be Hiroshi Nakatsuji, Gemma Solomon, and Markus Reiher, and especially you, Hiroshi. Welcome to the webinar.
Okay, thank you.
How are you doing today? I should say good evening to you.
Thank you very much.
Pleasure having you joining us here in Uppsala. Thank you very much for coming. Could you share your screen with us, please?
Okay.
Perfect. Could you go to
okay, thank you.
Could you go to full screen mode, please?
Full screen. Is this okay?
Yes, that's fine. Thank you very much, Martin, for assisting us.
Thank you.
So,
thank you very much.
Hiroshi, you have 40 minutes starting from now.
Oh, thank you.
The webinar is yours.
Okay, thank you. So, thank you very much for inviting me to this Löwdin lecture. This is the second time, and I'm very happy to be able to present this symposium. And the title today is Scaling Schrödinger Equation and the Accurate and Efficient Methodology for Solving the Schrödinger Equation, formulated therefrom. This is a, This is a slide from Löwdin lecture 206. And at that time, the host was Professor Lune, and I was invited with Professor Weinfeld, and I was given a gift from Professor Lune. And now our colleague, Dr. Hiroyuki Nakashima and Dr. Yusaku Kurokawa. And our purpose is to find the method of solving the Schrödinger equation as accurately and as easily as possible for performing chemical studies from theoretical side. Schrödinger equation governs chemistry. So, for a priori prediction of chemistry, accurate and efficient general method for solving the Schrödinger equation is necessary. But direct analytical solution of this second order differential equation is almost impossible for general atoms and molecules. So we start from studying structure of the exact wave function. We examine 3 equivalent equations. Schrödinger equation and the H-square equation is valid only for exact psi. only exact psi satisfies the two equations. But the variational principle is used to calculate best possible psi. So we can start from some approximate psi and reach, if possible, to exact wave function. Then let us examine this and that. When delta psi has this form, then when we put this into here, we get this equation, which means that when a psi, including only one variable c, satisfies this equation, then it has a structure of the exact wave function, because the variationally best psi satisfies this h-square equation, which is valid only for exact psi. So then, simplest psi that has a structure of the exact wave function can be written in these forms. This is simplest ECC formula, and this is simplest ICI formula. I use this formula today, and this is a recursion formula. You start from psi 0, psi 1, psi 1, psi 2 in such a way. And at convergence, psi n is guaranteed to become exact. This can be said that Hamiltonian of the system paves its own way to the exact wave function. So we want to use variation principle to solve simplest ICI formula. Namely, we put this into here, then the variational principle does not work because of the divergence difficulty. Namely, this integral comes just even from the beginning, but this integral diverges. For example, even for hydrogen atom, that problem occurs. For these two, no problem, but this occurs from first order ICI, diverge. And even from Gaussian orbital, again diverge. In such a way, we meet divergence difficulty. So the original Schrödinger equation does not match with the variational principle for the existence of the singular Coulomb potential in the Hamiltonian. So it is necessary to modify the original Schrödinger equation to match with the variational principle. I did that by introducing scaled Schrödinger equation, SSE, in 204. I put G function, I call it scaling operator, scaling function, in front of the Schrödinger equation. And G must be positive. And it does not satisfy this GH principle. And because this is always positive, you can divide this by G without affecting the solution. And so, SSE scales Schrödinger equation and Schrödinger equation have the same set of solutions. And G should not be zero at all configuration space except at singular points. But even at the singular point of V potential, G equals there, G equals 0, but GV approaching collisional point should not be 0 for not eliminating the information of Hamiltonian as a singular point. So many possibilities exist for G functions. A popular simple choice is this choice. Here, when I put GH, ICI was originally only this, but now I know G is necessary. So this is a scaled Schrödinger equation. Then, in this case, Gn is guaranteed, psi n is guaranteed to converge to the exact wave function without meeting any singularity problem at all. the free component theory, we can formulate free component theory from this. You proceed order n, then you have many complex analytical functions, etc. Then from SEICI or SICI of order n, choose all independent and non-diverging analytical functions psi I and give independent coefficient for each. Then we can write this into this. This is something like analytical essence of this function, which we call free component wave function. And this one, complement function, CL. And this converge faster to the exact wave function than original simplest ICI. So we want to calculate free component wave function. When we apply variational principle, we obtain this circular equation, and we have to calculate Hamiltonian and overlap integral, but in this case, without any singularity problem. And this is highly accurate and robust. And the integrals in closed form, analytical form, is, but for example, particularly for Rij type function, the integration is difficult. And also, integral storage is sometimes problematic. So we propose to use local Schrödinger equation method. The Schrödinger equation itself is a local equation. And here, this is local energy, and R is sampling points. And we choose some set of selected sampling points. And we can get variational analog of LSE method like this. It's very similar to the variational formula. And this is accurate when the distribution density of R mu is proportional to mu psi 0. This is a basic principle of sampling method. And this is integral free. It is easily applicable to complex two-electron functions. And the LSE method becomes more accurate as psi becomes closer to exact, because the fluctuation of epsilon R mu becomes small. When psi is accurate, this fluctuation of epsilon local energy should be small. Therefore, this theory is suitable to the theory near exact. The original Schrödinger equation, we have two ways of solution. One is free component variational. The other is free component LSE. We want to explain these two ways of approach. So first approach is free component variational approach. This is a helium atom. This is G function. Psi 0 is electron nuclear potential, electron potential minus, therefore this is always positive. And this is psi 0 first. And to first order, we already get chemical accuracy. Second order, spectroscopic accuracy, and very quick convergence. And on the 27th order, we get this. And at that time, Professor Schwartz gave very clever solution of variational calculation, and up to here, correct. But from here, the lower than this, so up to here, so more than 40-digit accuracy was obtained. This is the stringent local energy examination. This is a stringent test of the exactness of the helium atom calculation. when we use n equal 5 wave function, the local energy like this fluctuate very much. But when become 6, very small fluctuation, and at here it's almost flat. So we need this one. So when at here n is n equal 12, we can see this with this, and again we can see fluctuation. But here they almost flat, and here when we use that we can get this. Even with this we cannot see anything. In such a way, our wave function has a local energy quite flat. Suppose that we are doing a sampling method. Here, fluctuation is large. Epsilon r may be very different from sampling point, but here, very flat. Here, almost everywhere, epsilon r is exact energy. In such a way, sampling method is good for exact wave function. This is that one. This is for lithium atom and beryllium atom with variational method. At order 2, we can get chemical accuracy. This is a difference of the energy from exact energy, free component energy. It is less than 1 kilocalorie per mole, so we call it chemical accuracy. And beryllium atom, again, at order 2, chemical accuracy. So, and at order 5, we can get spectroscopic accuracy for lithium. This is excitation energy. For lithium, all the excited states are calculated highly accurately. And for S state, the accuracy is Kaiser accuracy. And the excitation energy for beryllium, again, a very nice 45-degree line. And this is free component RIG theory applied to carbon atom. This was done by Nakashima-san. And even at order 4, we could not get chemical accuracy when we use only linear RIJ. This is well-known property. And here we use up to 4 electron integrals. So but anyway, integral evaluations become more and more difficult as the system becomes larger. So we want to consider integral-oriented general theory within the free component theory, which we call free component SIJ theory. This theory was published very recently here. And in this theory, we choose electron scaling function Gij as Sij. Sij is this function. Therefore, EE cusp function, electron cusp function is not satisfied with this wave function. But we use this, so EN electron nuclear cusp function is okay. And the important thing is that Sij can be written only with 1 electron term. Therefore, free component wave function is written with only 1 electron functions. Therefore, all that necessary is only 1 and R12 to 1 and 2 electron integrals. Therefore, this can be done using only ordinary quantum chemistry code like Gaussian, Gamow, Morpho, etc. But we need usually higher order radial, angular momentum functions. But anyway, we can do by variational theory, and the free component theoretical framework takes care of the accuracy of the total wave function. This is a result applied to carbon atom, and we did a rather crude way, not beautiful way, and at the ninth step, we could get finally a chemical accuracy with one electron integral, 1-2 electron integral alone. And before I say that linear Rij could not get, but when we combine Rij with Sij, maybe we can get something. And here is the result. At order 3, by combining Sij assisted Rij, we could get chemical accuracy at order 3, not order 2. But anyway, you could get this result. And here we try to reproduce more stable using free component Sij theory. Valence excitation, we could get rather good result. Because excitation energy is a difference energy, therefore, even Sij theory can give rather accurate result. For Rydberg excitation, we could get quite accurate result within 0.01 electron volts accuracy. This is quite nice result. Here, we want to study C2 molecule. This is an interesting molecule. Oh, I'm sorry. People say that there is quadruple bond, namely 2s bond, px, py, pz bond, so quadruple bond. And from the ground state of carbon, we can get only double bond, sigma pi, 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 right? And from D symmetry, no bond can be expected. And we use that, and at the first order, Sij, we get this result compared with the accurate result due to Krauss-Reudenberg. You see our result, their result compare rather nicely. And further, we calculated for many, these are ground state region, many excited state region potential energy curve. And these are, they could be calculated rather easily with a free component Sij theory. And we also studied acetylene formation reaction, C2H, acetylene. And we calculated energy difference. This is a result. And blue is exact energy. Red is our result. These comparison is rather good. And in such a way, we could get some result from free component Sij theory. This is Löwdin with Joseph Noger at the Satellite Symposium ICQC in Bratislava. It was 1994, many years ago. I have a nice memory. I enjoyed very much. He smiles very nicely. He smiles very much. He was a organizer, one of the organizers of the symposium, very well organized. And so we have free component variation approach. And then next week, we want to explain free component LSC approach. I want to explore accurate GIG functions in order to make theory as accurately as possible by introducing accurate GIG functions. Then variational approach using integrals may become more difficult. But the LSC method becomes more accurate for the smaller local energy deviations due to the increasing accuracy of the wave function. Make functions as accurately as possible, then the LSE method becomes easier, accuracy increase. And the labor of the LSE method is almost the same and small anyway. So I want to generalize G into like this. This is 1 electron part, 2 electron part. But this G must satisfy some limiting conditions. At collisions from the cusp condition, both should have this expansion, Maclaurin expansion form. First should be Rij. And at infinite separation, no collision occur. Therefore, when no collision occur, G is unnecessary. Therefore, G must be unity or some constant. That's second condition. And when G function satisfies two conditions, we call that correct function, correct GIJ function. When it satisfies only condition 1, cusp condition, then we call that reasonable GIJ function. And when we use Sij function that do not satisfy cusp condition, therefore approximate. This is an example of correct GIJ functions. This satisfies both conditions. And these functions, as far as I know, Professor Nguyen and Bartlett use this first. And Tendo-san, he likes this function very much. Maybe I call this Tendo function. And these functions are also examined very nicely by Professor Hirata So-san. Anyway, these functions has a long history anyway. And we did, because we know these two conditions, mathematical handbook is enough to find such kind of functions anyway. And this is a R GYJ, and these functions are correct function, and this a reasonable function behave like that. And this is a set of GIJ functions we examined. And this one is ordinary one. This is not correct anyway. And this one, and this one. A sign function can be used anyway. And this is approximate, or Sij, defined with Sij. And we fixed parameters in the GIJ functions using helium atom. All the integrals were calculated using Maple program. That can be done very easily for helium atom. And the initial function was closed shell and this. And this is a result, variational result. And you see, this is correct, approximate, reasonable and approximate. And this one is most important anyway. And order 1, only 3 functions, correct, not chemical accuracy, but from order 2, we can get chemical accuracy, very stable result. This is order 3, one order of magnitude smaller than this one, and this 2 orders of magnitude smaller. And this more correct, less correct order. And you can see R12 is here. So worst of correct and reasonable function is R2. This is much larger than this, okay? This is much larger than this in such a way. So R12 is not very good choice anyway. When you use multiple function, 2 correct function together, then you can get better result. when we compare, this is 0.01 region, but this is 0.02 region. So this is better. That improvement is obtained using multiple functions. This is I cannot read. Cusp value. And you see, only this is enough. But should be minus 2.0 electron nuclear, all close. Electron 1.5. These are close, but this close, but not so much, and this approximate. Similar result. And we want to calculate free convert LC calculations. We use LC now for small atoms and molecules using general GIJ functions. And I assume transferability of GIJ functions from helium atom. Same GIJ used. And we did rational sampling up to anti-symmetrization of psi. These are the initial functions. Our initial function is VB type, and but the orbital is a bit nice behavior. So this is our initial function, energy of initial function. This is almost Hartree-Fock limit, MacLean-Yoshimine result. And our result is lower than this one, and by this kilocalorie per mole. And this is a result for that, for part. And for this, this is lithium atom. And you see, again, worst result was from R12. We could not get 0.0 result for even for n equals 3. For all others, we could get stably this accuracy. And when you use two correct functions together, you can improve this. This is n equal 2 result. This is improved to this, and this is improved to this. In such a way, when you use two correct functions, then you can improve the result. But the timing, our calculation took only 45 seconds single, or up to 2 minutes, 5 minutes. But variational method takes 3.7 hours, much faster. This is for beryllium. I'm sorry, this is similar. This is beryllium. And again, worst result comes from R12, and others nicer than this result. And this is n equal 2. And when you use double set, you can improve this to this and this to that. And in such a way, and timing is like this. If I showed earlier, previously, this result, it took 8.6 hours. But in our case, only 11 minutes, 31 minutes, etc. Anyway, much faster, so much easier. This is a sampling. I cannot see the title. This is sampling dependence. I examined VB type psi 0 as a basis of rational sampling, and Hartree-Fock orbital as a basis of rational sampling. They give very similar result. VB, Hartree-Fock gave essentially same result. You know these two are already very nice. And this is difference. So difference very small. So this shows sampling dependence is small. And the energy, we compare energy, variational energy, sampling energy, compare nicely, okay? And beryllium, okay, again, nicely. Carbon, sp3 again nicely. In such a way, more efficient, but energy is correct anyway. And next is molecule, lithium H, hydride, lithium 2. And our results again similar. Lithium hydride, this is order 3, very stable result altogether. And this is for lithium 2. And the timing is just a small 2-3 minutes. So this is in summary, but I have to finish now. And anyway, I talked the frequent LAC method using rational sampling procedure was efficient in both accuracy and computation labor. So we want to proceed this type of methodology further. And this is acknowledgement. This paper is attributed to the late Professor Keiji Murokuma for his long-term encouragements given to Hiroshi Nakatsuji. It's very sad. Anyway, all calculations were done using the super parallel computer at IMS Computer Center, Okazaki, Japan. We acknowledge here for their continuous support. And from funds from scientific funds, and also thank you for your attention. Thank you very much.
Thank you very much, Hiroshi. This is really impressive what you can do. I would again urge our attendants to use the Q&A option in Zoom, and I saw here a question came in. So let me read it for you. It's from Kong Wang. Question 1. For the FCRIJ-SIJ method, how many electron molecular integrals with R12 was evaluated? And question 2, what is the nature of the rational sampling?
Okay. The first one, when we include Sij together with Rij, we have to calculate many integrals. And because it includes Rij, it takes a lot of time anyway. And so Sij theory is a theory to use only for Sij. When it combined with Rij, the applicability is not good anyway. And many integrals we have calculated. And second question, rational sampling.
What's the nature of the rational sampling?
Rational means we do not use iterative method. And we use inverse transformation method from VB or VB anti-symmetrized function. Initial psi zero anti-symmetrical function, and from that we calculated by the inverse sampling method the rational sampling. So we do not do any iterative method like Metropolis procedure. It makes method computation time shorter.
Okay. And the final question here is from Dag Sundholm in Helsinki. He says, do you see relativistic effects when comparing to experiment? Can your methods be extended to the direct equations?
Yes. We for lithium and beryllium, we did very accurate calculations, and the comparison with experiments was just to see relativistic effect. The difference was mostly relativistic effect. And we applied our theory to relativistic Dirac-Coulomb Hamiltonian. And in that case, we applied so far only to helium atom, 2-electron system. And maybe we have to extend more, but we are busy now to Schrödinger type programs.
So thank you very much again for your presentation. And again, the attendees can still ask questions to Professor Nakatsuji down in the Q&A you have down in the bottom here. And I ask Hiroshi to answer the questions down there. And with that, we move on to the second presentation, which is by Gemma. Are you there, Gemma? Oh, there you are. I can hear you too.
Let me just share my screen.
So Copenhagen is calling in.
Copenhagen is calling in, indeed. After technical difficulties earlier that you saved me from.
It's great, and we can hear you loud and clear.
Lovely.
Yes, so you will have 40 minutes, and then remember we have a Q&A afterwards.
Great.
Pleasure having you here.
Thank you. Thank you very much. So thank you for organizing this nice meeting. I know when we got the email about it and I forwarded it out to my colleagues, I got nothing but positive response. And I think people, with 2020 being such a quiet year for conferences, people are very eager for such a nice meeting coming together. And I'm looking forward to the rest of today. So I'm offering a little bit of a change of pace this afternoon because I do not work on such sophisticated, elegant methods, pushing the limits of theory in these kind of ways. We work with, I guess, probably what is in this community really the quick and dirty end of calculations, predominantly density functional theory. But I think what our real sort of focus is on is working out, understanding chemistry and where in chemical space do we really see unusual effects in molecules, and what's the limit of some of the unintuitive effects we might see in molecular systems. So what I'm going to be talking about today is some work we've done. Goes back more years, but particularly in the last few years, looking at molecular insulators. And I change the title periodically. Sometimes I say, how low can we go? And sometimes I say better than nothing. And I think I actually submitted this abstract with better than nothing. And I'll tell you why I think this system is actually better than nothing. So just to give everybody a sense of the systems we're dealing with, the experiments we're talking to, because not everybody's familiar with this, our corner of the nanoscience world, we're dealing with single molecule conductance measurements. So obviously, if we want to know about a molecular insulator, we want to know how current flows through that system. And the experiments that are typically done or very popular is what's known as an STM break junction. So whereas I guess many people are familiar with STM, where we sort of scan on the surface and you have some image generated from the tunneling current. Here instead, there'll be again a surface and a tip, but instead the tip is crashed into the surface. And if you do that in gold, sort of gold substrate, gold tip, gold is actually a metal where under-coordinated gold atoms have stronger bonds than the bulk. So you can imagine, so you crash this tip, you retract it again, and in the sort of region where you have some sort of small number of gold atoms, you've got some sort of little point contact that's forming. As these gold atoms we have in this narrow region are actually stronger sort of on a single bond level than in the bulk. So you can have the situation happening a bit like in this cartoon, where you actually pull out additional atoms from the bulk rather than breaking that point contact. At 4 Kelvin, they'll see these type of systems where they'll get these sort of single atom thick gold wires forming. At room temperature, which is actually where this experiment was performed. That's a fiction. At room temperature these days, people say they'll get a single atom gold point contact, but they won't see, you know, a long gold chain pulled out like this. But if you measure the current through this junction while this is happening, gold is a system where the current or the conductance is quantized, and for each gold atom you have in the sort of smallest cross-sectional area, you get what's known as 1 g0, a quantum of conductance through the system. So this is what's known as a conductance trait. So as they're attracting this tip, and you can see that we've got a conductance of 3, and then it steps down to 2, and it steps down to 1. And that's where we're going from sort of 3 atoms in the smallest cross-sectional area, and then that junction's being pulled, and at some point it's going to 2 atoms, and then at some point it's going to one gold atom, little point contact. And if you pull that junction further and do this in a solution of molecules, then down in this region, which sort of looks like it's the noise on this scale, you look in there and then you see there's other kind of steps. These are not as neat and not as regular as we saw for the gold, but this is actually the steps of, you know, in molecules now. The cartoon shows you here but being bound in the junction. And if you do the same experiment without molecules that combine in the junction, and so that could just be under ambient conditions, or it could just be in sort of a solvent that doesn't have binding groups, so it doesn't have a strong interaction with the gold, then you'll just see something like a tunneling decay curve. So this is the experiments that allow us to measure molecular conductance. But of course, you know, while the steps here were nice and regular, the steps here were not so regular. So you have this question of, well, how do you actually quantify the conductance of a molecule? And we do that by making histograms. So all of this data, you know, is sort of summed together. We flip the axis around. So now we have conductance on the x-axis, counts on the y. We make histograms. And of course, in regions where you have a step in the conductance trace, you have a whole lot more counts. And so that translates into a peak in the histogram. And can fit these peaks to Gaussians, and you're recording the conductance of the molecule, you know, on the basis of these fitted peaks. So that's the experiment, and that gives you a sense of the sort of dynamic environment and some of the picture of the challenges of contacting a single molecule to measure conductance. And then so you could say, I mean, this is a challenging problem for theory in the sense that we can't do it with traditional chemical methods where we're concerned about the molecule alone. We have to be sort of equally concerned about how we're treating the electrodes, the big gold, and they have to look like gold metal because then we need a good description of the Fermi energy. So we're looking at bulk, you know, really significantly sized gold electrodes. So this is sort of what pushes us towards the cheaper end of theoretical methods. We typically use DFT. I think pretty much everything I'll be showing you today is actually just done with PBE and double zeta basis set, really at the cheap end. But this is the level that allows us to have sort of significantly sized gold electrodes with periodic boundary conditions and a sort of decent description of the density of states of those electrodes, as well as, you know, a somewhat compromised but a qualitatively useful description of the electronic structure of the molecule. So rather than the sort of complexity of this experiment, we typically study molecules in relatively simple geometries in the junction. This cartoon shows a molecule bound to a flat surface, but sometimes we'll also, you know, have little pyramids on the surface. With this sort of system, we calculate a few different things. You'll see a lot of, we calculate what's known as the transmission. The transmission through the system is a probability per channel for the electron to be transmitted, but it's possible that there's more than one channel in a molecule. So it's a probability in some sense, but you're sometimes seeing it go above 1 because it's the total transmission for the system. And the transmission of particular experimental relevance is the transmission around the Fermi energy of the gold electrode, and most of the plots I'll show here are plotted relative to the gold Fermi energy. The other thing that we plot Sometimes we call sort of interatomic currents or local currents through the system. It's a tunneling process we have here, but we can decompose it in the spirit of a lot of chemistry, chemical theory, into sort of interactions between pairs of atoms that mediate the tunneling current. So we can draw these kind of pictures and look at, what interactions in the molecule are responsible for the tunneling current. Don't be mistaken. I mean, while it sort of this picture gives the impression of an electron hopping through the molecule, it's not. This is the interactions in the molecule that describe the lowest tunneling barrier for an electron passing through the system. So that's the background of where we are. What are we interested in? And so I said insulators. And from a sort of practical point of view, you can say, well, why are you interested in insulators? But as much as, we have this rhetoric about miniaturizing electronic components, and that is certainly of significant interest, almost a more sort of profound challenge is that of minimizing leakage currents. So here we're talking about in transistors, the dielectric materials that are used between the gates and the channel. And you start to ask the question, how do what is the optimal way at a 1 nanometer, few nanometer scale to really minimize current? And here, we have seen these sort of interference effects in molecules, and this smells like something that might show promise in that direction. From a fundamental sort of science point of view, it's also just very interesting to say, what's the limit? How can we take a junction, fill it with a molecule that, is full of, electrons. We imagine we've got sort of continuous electron density across this junction, but in such a way that there is no possibility for current, for electronic sort of communication across that junction. So this is where the better than nothing comes in. So in a cartoon sense, this is the picture of our system. We've got some incoming wave, we've got a molecule as the tunneling barrier, and some outgoing wave. And the natural limit one thinks of for this kind of system is vacuum. You say, well, if we imagine that we can, really we attenuate the wave function to a significant extent if we don't have anything in that junction. And so that's, for some given length, that describes a system that seems like an optimally insulating system for a tunneling problem. So, of course, this is the goal then. Can we beat a vacuum gap of some particular dimensions? And, of course, because in the vacuum gap, there is the decay of the wave function in space. And so can we design a molecular system that somehow suppresses tunneling more efficiently than vacuum? Okay, so this is, putting it into more, less cartoonish terms. We can, we know a simple barrier tunneling problem, and depending on the height of the barrier, we're going to see that, the exponential decay changing, and this is, we're plotting now the transmission as a function of length. So, of course, when we go to molecules, we don't have, a continuous length distribution, but, for some system, an alkane, we can, increase the number of carbon atoms in the chain. And what we get is, then shown on the right here for the transmission, depending on, n we have here for the number of carbon atoms. As we increase n, the transmission at the Fermi energy is dropping linearly on a log scale, and it's our same sort of exponential decay of tunneling as a function of the increasing length of the system. So to overcome this kind of paradigm, we have to have something else in play. And what I told you before that we've been interested in is quantum interference effects. So this has been seen and known of in various forms in conjugated molecules to a significant extent. One of the most well-known systems that we could be considering would be something like a meta-substituted benzene ring. So again, now, in this picture here, we have this sort of sense of different orbital contributions to the transport. Now we've got something similar, but if we look at so now the black curve here is giving us a sort of cartoon picture of the total transmission. The red curve here is giving us the sigma channel, and the blue dashed line here is the pi path, or the pi channel. And what you can see is at the Fermi energy, the contribution through the pi system for this meta-substituted benzene goes to 0. So this is a quantum interference effect. Sometimes we call it an anti-resonance, sometimes I'll probably call it an interference feature. But it basically gives us a hint that, if you can really with interference, make the transmission go to 0, that seems like something we could use to beat vacuum. So when we have this possible space, chemical space for molecular insulators, and you ask a chemist, where's a good place to start for insulators, many people will suggest an alkane. And indeed, alkanes were typically used as the sort of saturated counterexample for many molecular wires type studies, when people were trying to develop highly conductive molecules. And so things get a little more complicated than the picture I told you before, when people started trying to do these STM break junction experiments on alkanes. Because instead of seeing, just a few peaks for this molecule, they suddenly saw all kinds of peaks at different conductance values in the conductance histograms. And so what was hypothesized there is, well, it might matter, the binding geometry of these molecules in the junction. So in here, it's sort of showing the idea of the sulfur atom interacting with 2 gold atoms versus the sulfur, sitting directly on top of a single gold atom. And then versus the situation where, rather than having, our all-trans extended structure here, we instead have some sort of Gauss defect in the system. And it was hypothesized that this was the highest conductance, this was sort of an intermediate conductance, and this was the lowest conductance. So that sort of explanation is very hard to get at by experimental means. But with a calculation, we can control that central dihedral angle for an alkane. So doing something like that and plotting the transmission. So here we're going from the all-trans alkane, which is, up here, this sort of black near the brown and the red curves. And then as we take that dihedral and we twist it around, then we drop down. And the transmission here is dropping by orders of magnitude. So this looks significant. But if we just start with, the all-trans, our extended structure, our lowest energy structures for our alkane, what's our expectations? So this is the picture we have here. So now we're plotting experimentally measured conductance versus theoretically derived sulfur-sulfur length of the molecule, with the idea being that the ultimate insulator is the lowest possible conductance at the shortest possible length, okay? Because we know that, just increasing the length, we expect some exponential decay. So this is the line we get for the alkanes. And so this forms the sort of the basis of, what's our space, what's our goal? And so then the question becomes, how far we can go down into this lower left corner. And this gives you a sense of, where some other molecules that people have been interested in appear. And one of the systems I highlight here is if you look at what these are silanes. So again, saturated systems, they're permethylated, there's little methyl groups up here, but it's a silicon chain rather than a carbon chain. And you can see actually that the silanes are longer, but also significantly more conductive than carbon systems. Okay, so if you ask a physicist, And one often gets interesting answers for suggestions for molecules when you ask a physicist. But you could ask a physicist where they would choose to look for a highly insulating molecule. And one suggestion comes back, well, silicon dioxide has served the world very well as an insulating or dielectric material. And if we look at that system, we see the characteristics sort of silicon, oxygen, silicon, this repeating motif through the structure, and that can be translated into something like a molecule, and these are called siloxanes. So what you see repeated here is again a silicon, oxygen, silicon motif through the molecules, and we have some binding groups on there, and we can vary the length of this part. So when I have people in a room, I always like to do a show of hands for this question. And at least in my experience, what I've found is interesting is our chemical education doesn't necessarily prepare us well to answer a question like this. If we want to say, electronic communication in an alkane versus a siloxane, there's sort of an argument for both of them being insulating systems, who's going to win. And typically the results are split about 50-50. So this is the experiment. We see some nice peaks in a conductance histogram for the siloxanes, and this is what they saw. So now you can see there's the silanes that I told you were high, the alkanes that are lower, and the siloxanes are significantly lower. So these are not only lower conductance for the particular length, but they also exhibit a steeper decay. So this is typically called the beta value. So how fast it's decaying. They also have a steeper decay than the alkane. So these are really highly insulating molecules. So this is what comes out of the calculations, and this gives you a sense of the sort of agreement or disagreement, what we should say, but between theory and experiment here. We are certainly nowhere in the ballpark of chemical accuracy. Really, I believe strongly the goal for this kind of work is qualitative agreement rather than quantitative agreement. We don't even know, the details of the atomic structure that's being measured in the experiment. So quantitative agreement is a very funny goal to have in that sense. So it's a different sort of philosophical approach. And you can see here, we certainly capture the broad trends that we're seeing in the experiment. So then, of course, the question is, where are we on this plot? And what we see here is the siloxanes, as I said, they're into our blue region, they're low, but of course, we're interested in seeing if we can push even further below the system. So I promised you something with interference, and that's where our next strategy comes in. So there was the systems with pi interference. So this is another type of system where we see interference in the pi system. It's called a cross-conjugated molecule. And I guess the reason that the pi systems aren't good enough is, of course, we have underlying sigma transmission. So we want sigma interference, we want to have a saturated molecule with significant destructive interference because we want everything to be switched off. So one of the useful things that we learnt out of our sort of studies of interference in conjugated molecules is what other signatures are there of an interference effect. And this is where these sort of local transmission or local currents, interatomic currents come in. So what I'm showing here is the transmission here in black. This dashed line is just for the pi component. And up here, we've got these coloured arrows that are sort of pointing to a sort of particular domain down here. And we see a characteristic picture of the local current. So this is energy dependent. This local transmission element sort of matters where you are in energy. And as we sort of move through different resonances of the molecule. But the critical thing here is every time we have one of these interference features, so we've actually got 3 in this molecule. We've got this one near the Fermi energy with the blue line, but also sort of out here near the resonances, we have these two red lines that are marked here. And if you look, to the left of this red line, you see a sort of ring current that's, clockwise direction around the whole benzene ring. We go to the other side of the interference feature and we see the same ring current, but it's reverse direction. When we come to the interference feature at the Fermi energy, we see the same behavior, but now it's a different, cyclic current. So it's a counterclockwise, ring current, this around these sort of 3 carbon atoms here, 2 of these. And again, we move to the other side and those ring currents have reverse direction. So this gives us a sense that this is something else we can look for when we're trying to find an interference effect in a molecular system. So I told you before that we saw this significant suppression of the communication, the current through the system when we messed with this central dihedral angle in saturated systems. And you could ask the question, well, is this the interference effect that we're looking for? Is this sigma interference? Because we have this significant suppression, but we don't see that sort of sharp feature of the transmission going to 0. But of course, you can have, sort of a interference effect in some components while some other components are still transmitting. When suddenly you're looking for an effect, something going to 0, all kinds of other small contributions can mess with things, and things that you don't normally worry about might become very significant. So in this case here, we can do the same analysis with the ring currents, the local currents, and what we see now, if we take this system where we've really twisted it around, so now our central dihedral is around 0, then we see now we look to the left of this dip and we see a clockwise sort of ring current through the center of the molecule, and to the right you can see, there's a variation, but all of these little ring currents are running counterclockwise. So this gives us a sense that this dihedral dependence in saturated systems is actually giving rise to an interference effect that's messing with the electronic communication through that molecule to a really significant extent. But of course, this is a high energy structure of this molecule. This is not, something we would expect to be readily measurable. So if we do the same thing in silanes, we go from these higher conductance saturated systems to something with actually an even more pronounced interference effect. And looking at these plots, you think, this, I can buy that this looks like, transmission going towards 0. So how do we make this measurable, given that this is not, a nice minimum energy structure for these molecules? And conveniently, this is, where synthetic chemistry comes in, and it turns out that if you make these bicyclic silane type structures, we have actually 3 bridges, through the system, and each of these paths have this, unfavorable dihedral angle that we want, this dihedral angle very close to 0. So this is, this sort of structure. You've got this cage kind of structure. And of course, we can compare the current or the transmission through this molecule with the linear silane of the same length. So this is what they look like. This is the extended silane and the cage structure. So if we calculate the transmission through these systems, you see that indeed the cage structure, we have a significant interference dip. It's not right at the Fermi energy, but it's not so far away. And over, a large energy range, we see suppression of the transmission. If they do the experiment, they see pretty much the same effect. They see, again, significant suppression of the conductance in the cage structure, the 2-2, this we're calling 2-2-2 structure. But I promised you something better than vacuum. So this is the next dimension. And this is, again, where, the advantages of theory come in, because we can make a little vacuum gap. We can cut the 3 bonds. We can remove these central silicon atoms that are forming the 3 bridges. We simply passivate the bridgehead silicon atoms with hydrogen, and then we can calculate the transmission through this system here, where we essentially have, a gap through the molecule. And we can set that initially at being the same distance as the 2-2 structure, but we can also vary. So this is what we had before, with the 2-2 sitting below the linear silane, and this is now what we have for the cut system. So you can see that across, a really significant energy range, we've removed all of these 3 paths, these 3 bridges, and the transmission has gone up. So we have much better electronic communication across that molecule without the bonds in place. And what's more, if we want to stretch the cut system to reach the same low conductance we saw for the 2-2 system, we have to stretch it another 1.5 angstrom. So this is, carbon-carbon bond dimensions, sort of extra gap to have a suppression of the transmission down to the level of the 2-2 system. So we thought this was certainly interesting. So where are we on this plot? And the answer is here. So this 2-2 molecule I've told you about, it turns out it's slightly, very slightly below the line I would draw between the 2 siloxanes, but not a lot. So it's a different chemical strategy. It's interesting to that extent, but it's certainly interesting to know, how much further we can go still. It still feels like there's space to push things lower. So I can see that I have only 5 minutes to go-ish. So I will jump ahead a little bit and go over the last part very quickly. The first, we sort of investigated 2 sort of things in this question of, okay, so chemically, how low can we go? And the first thing is, how sort of generally insulating is this motif, this bicyclic cage motif? We can do that by just, screening a lot of structures, varying the constituent atoms here between carbon, silicon, and germanium. And so what you see in this is a distribution of the transmission of the sort of approximately 800 molecules that we looked at here. And you can see that the 2-2 structure is low, but not the lowest. You can see there's a significant variation, but there is sort of space. We've got an insulating class of molecules to play with. But, what we would really like to find out from this is, what matters, the structure, function, type relationships, how chemically should we design the optimal insulator out of this motif? And that's when things get really tricky, because it turns out that, we see things like in the difference between our, worst insulator and our second best insulator comes from just shifting 2 atoms in the system. So you can see over in this case, we have a mixed silicon and germanium bonds in 2 arms and an all carbon arm here. Here we've got an all silicon, all germanium, and all carbon arm. And that is, making a massive difference. So it seems that the bond lengths, the bond angles, all kinds of details of the structure, perhaps unsurprisingly, small changes matter when it's an interference effect. You can imagine in a 2-slit experiment type picture, a small change in our 2 slits and the interference fringes can change significantly. We also were interested in the question of why carbon didn't seem, the all carbon structures were pretty rubbish, actually, insulators. And we realized that in the comparison we were doing here, we were changing more than the backbone atoms. So typically when you do a silicon or germanium-based structure, they're methylated. And when we do the carbon structures, we put hydrogen on. And it turns out, and I'm going to skip completely over these results, but the methyls matter. So the methyls, we would have thought, were just a benign substituent that wasn't doing much to the electronic communication through the system, but the methyls seem to have a significant impact, at least in these systems, on the interference effect. So, in conclusion, we'd say chemical space offers some very interesting possibilities for molecular insulators. The siloxanes should not be forgotten. They were very effective insulators over a broad range. Maybe not so interesting from a fundamental science point of view because it's much easier to understand that interference feature. The interference effects, particularly in these saturated systems, are much more challenging to understand. So we have this 222 sort of structural motif that's very effective in shutting off electronic communication, but we don't know exactly what matters in controlling these systems. So that's an open question, and there's certainly scope for more work there. People that did the work, people who have paid for it, thank you all for your attention, and sorry I've gone into my question time.
Thank you very much, Gemma. This was very interesting, especially the end, you know. You showed this bicyclic compound. Actually, the very first molecule I published with Bjorn was on the bicyclo 221 octadienyl molecule. So, So you might be interested. The 221. I mean, if I take that as a question for them, there's that the 221 will look just like the all-trans alkane. The 221, as soon as you change one of those linkages to just a single atom, you'll end up with this highly conducting pathway through the whole system, and that completely changes the transport property. I was also, when you was discussing the conductivity, I was thinking about there's something in hydraulics which is called a Tesla lock. Are you familiar with that?
No.
So it's a device which you can send flow through in one direction, but if you try to do it in the other direction, it's going to stop.
Okay.
And it's sort of designed that it sort of have loops that goes back. So it bifurcates and goes back. So if you go in this direction, you're going to have the two streams meet each other. Whereas if you come in from this direction,
you don't see the loops.
It goes through. Anyhow. So you might consider that scaffolding.
I mean that would give us a rectifier, right? So here we were just trying to shut everything off.
Yeah, but here you would have it unidirectional.
Yeah.
Here's a question. Here's a question from the Q&A. Hi, where exactly would be the vacuum in your graphs as compared to the alkynes? I missed that.
Yeah. It's not there. It's not there. We tried so hard to put it on there. So we could have the vacuum in the calculation, right? We can say, okay, for the calculation we have to worry about making sure we have basis functions in the gap so that we can have that describe the decay of wave, that we can do it. But that graph, this sort of plot we have with the blue part that we're trying to get into was all experimentally derived conductance values. So when they do this experiment, they're pulling this gold wire, and then at the point that it breaks, there's this sort of like the structure will relax a little bit. So at the point that it breaks, you don't have a 0.1 angstrom gap. You have, I think, 6 to 8 angstrom gap. So the vacuum, if you wanted to do something like vacuum in that experiment, you would have to go, towards the surface rather than away, because you don't know, you can't calibrate the distance.
Yeah.
You can calibrate the distance on a relative scale, but not on an absolute scale. The other sort of complication is these experiments are typically done under ambient conditions. So they say, okay, you could do that, but you're not measuring the vacuum. You're measuring water or solvent or whatever else is in there. So, and the third trick, if you want to call it that we showed here, is, we were not beating vacuum of the full junction. We were really only beating this fake vacuum between the bridgehead silicon atoms. And of course, they can't do that experiment. We have some systems now where we think we, can push it down to beating the vacuum gap of the full junction. But it would be a different kind of experiment to be able to have an experimental vacuum line compared.
We have time for one last question. It's from Julia Emilia. For applications in molecular electronics, it would also be very interesting to be able to control the conductance through the junction. Do you know if there are any easy way to control the conductance of these molecules, for example, by electric fields or strains?
Yeah, so these saturated systems, we haven't explored to a significant extent the control, because I guess here we've really been just going for insulators. But more generally, the sort of interference effects in the conjugated molecules, I mean, what's very nice about the interference effects is, we are dealing with this sort of sometimes very sharp feature in the transmission. So we switch the current off, but it's only a very sort of limited energy range. So some perturbation to the molecule, it can be electric field. We haven't tried strain. The junctions themselves, the gold itself is very soft, so I don't know about strain. Chemical substitution, sort of electrochemical gating, there's lots of things that will shift the interference feature around. And so people have done those types of experiments. Chemically and electronically, you can certainly shift the position of these interference features, and that's going to turn the current on and off.
Thank you very much. Thanks for your presentation.
Thanks for having me.
Oh, you're welcome. Our pleasure. So with that, we move on to the third presentation for this fourth session of the symposium, and I welcome Markus Reiher to the webinar. Are you there, Markus?
Yes, I'm here.
Oh, pleasure having you. How are you doing today?
I'm fine. This will be my first talk being delivered while I'm sitting rather than standing.
Well, it goes with old age. When you get old, you have to start to sit down when you're doing your presentations. So it's our pleasure to have you here. If you could start sharing your screen with us, please.
Thank you for having me. Here we go. And so,
and if you could go over in full screen mode.
Yeah, I can't. I don't know why that is. This is new.
Oh, there it is. Perfect.
Excellent.
So the next 40 minutes, you have all attention from the audience. Go ahead, please.
Thank you so much. Thanks again for having me, being part of this interesting symposium. I really like this. And from the title of my talk, you see that it relates to other talks in the symposium. So I will be talking about multi-component quantum chemistry, and naturally, it connects to Sharon's talk of yesterday. It has a different focus, though, and so I hope that you enjoy it, the extension of the topic. And also, it relates to the first talk of today, as you will see. So let me tell you a bit more about my topic. So multi-component, of course, refers to the fact that we intend to describe different elementary particles, and I count atomic nuclei as elementary particles for the sake of simplicity, and given the fact that we do low energy physics, that should be fine. So it refers to the fact multi-component, it refers to the fact that we want to describe on the same basis, basically different sorts of particles. And for that, we use explicitly correlated wave functions. And we intend to not only go for a non-relativistic, but also for a relativistic description, which also connects to questions that were raised today. And the framework in which we are doing this is first quantized quantum mechanics, or as it sometimes is called in physics, semi-classical. So we have a quantized matter field, but a classical radiation field. Actually, this whole thing started out of a fun project. And so we just wanted to learn more about general type of wave function that can be used for a set of arbitrary composition in terms of particle type. And so we go for geminals, and we implemented a stochastic optimization scheme for all parameters. So the optimization is nonlinear. And we intended to not do only Born-Oppenheimer, but also what we call pre-Born Oppenheimer, and often it's called just non-Born Oppenheimer calculations. But I always felt that non-Born Oppenheimer sounds a bit strange because you called something after an approximation that you not intend to do. But given the fact that the Born-Oppenheimer approximation is central to what we do in chemistry, actually, I think pre-Born Oppenheimer was for us a very good term. Let me make another comment on this issue, because I will come back to this later in my talk. The fact that we use the Born-Oppenheimer approximation has two major consequences. First of all, of course, it introduces in a very intuitive way molecular structure, or in a sense, it imprints molecular structure on our theory. And so one might wonder how to actually recover molecular structure from theory that does not apply the Born-Oppenheimer approximation. I will come back to that topic later on. The other point is that the Born-Oppenheimer approximation allows us to very efficiently do calculations and then later correct for the deficiency of the approximation itself, as you know. One of the other main reasons why we look into this is because we wanted to study the electromagnetic interaction of all the charged particles, so between the electrons and between the nuclei, because as you probably all know, if you work in the non-relativistic regime, which is considered to be one where the speed of light is infinite, then there are no magnetic interactions at all. And so the electrostatic Coulomb interaction would be exact in the non-relativistic world. And the moment you have a finite speed of light, magnetic interactions become important. And then the question is of how to include all electrostatic, magnetic, and retardation effects in our Hamiltonian. And one operator that is famous is in relativistic quantum chemistry is the Breit operator, which approximately considers magnetic and retardation effects. And the question is, how can you push this further? And the reason for that is given here in my fourth point. In experiment, you can measure things like the binding energy of two hydrogen atoms, which is the prototypical bonding energy, right? To an insane accuracy. And calculations have a hard time getting there, and only few groups have accomplished this to match the experimental accuracy. And the question is, and that has been done in a very specific way with very accurate non-relativistic wave functions, and then in a series expansion in terms of relativistic and QED, especially QED operators. The question is whether you can do that from a first quantized semi-classical framework where everything relies on the Dirac equation. That was another motivation for the work. And in the end, you will see that we need to return to orbitals, and I will explain to you why we do that. And in fact, we combine this orbital model for the nuclei and the electrons with calculation of state interaction parameters through the density matrix renormalization group, DMRG. So this is kind of the overview for my talk. And let's get into the details. I have a couple of slides on technical details because the whole theory is really cumbersome. So it is annoying to develop and implement this. Also, you need to develop all the integrals, find ways to make sure that the integral implementation is correct and so on. So this takes some time. And in fact, we are working on this now for 10 years. And one of the reasons why it takes us so long to make progress is that the technical intricacies are actually enormous. So let me start with on this slide here. Up here, you see the general form of the wave function, right? Basically, it's kind of a CI type expansion, but you need to keep in mind that our basis functions, the phi here, are many particle basis functions, and they are wave functions for all particles in the system. Okay, not only the electrons, also the nuclei, and they can be combined with some function that considers additional information. And here you see it's a spin function. And naturally, if you go for a relativistic basis function, then that will look a little bit different. The point is that in front of it, there's an anti-symmetrization or symmetrization operator, because we need to make sure that all collections of like particles are properly symmetrized and anti-symmetrized. And then there's this state in the interaction parameter CK. Okay, let me explain you a little bit more detail our basis functions. So you see here, one of the many particle functions. They are Gaussian geminals for the simple reason that we need to be able to analytically evaluate the integrals. They are written in a form that takes some time to get used to. So that's why on the right-hand side, I wrote the same function, split it as a product of Gaussian functions, as you can see, with the individual coordinates. And these position vectors are referred to all the particles in the system, no matter whether they're electrons or nuclei. And so these are plain ECGs, plain explicitly correlated Gaussian geminals. And naturally, in these functions, we don't have any angular momentum information, right? And in order to have an efficient basis set, you immediately would raise the question, well, wouldn't it be possible to include that information in order to eventually get a very compact wave function that does not need as many basis functions of this type than a plain ECG basis would need? That's indeed possible. And here we follow an idea by Suzuki and Vargas, which is called the global vector representation, where rather than coupling all the angular momentum properly, we have a global vector that is defined and with a couple of parameters, and then employed as a prefactor in this basis, and that works pretty efficient. Sharon mentioned this already yesterday. The elimination of center of mass motion is, of course, key because it deteriorates the energy. Typically, what you would do is you would transform to a set of translation invariant coordinates, but that would change your kinetic energy operators. It would make all the integral evaluations difficult, and the parameterization, the calculation of the parameters, difficult too. We figured out that with our basis functions, it is actually possible to add and this is shown here in this scheme in the upper half of the slide, that it's possible to make the to accomplish the removal of the center of mass contamination at the level of the expectation values. So you can do a transformation which in the end requires you to subtract a well-defined analytical form from the expectation value that guarantees that the expectation value is not contaminated by center of mass motion. And the key here is that the integral evaluation itself is still possible in laboratory fixed LF Cartesian coordinates, which is, of course, convenient for efficient computations. I can show you that this actually works. In this slide here, where in the table you see two systems, it's H2 plus and H2 in the ground state. You see in our calculation, we use NB as the number of basis functions, first for the cation 180 basis functions, and for H2 500 basis functions. If we don't do anything and we just evaluate the integrals without correcting for center of mass motion, we get these energies here. Then the reliable energy values are given in the second column, and you can see easily by comparison that the contamination of center of mass motion is significant, and so it's obvious that something needs to be done about. And we compare also with data from the literature for H2 plus with data from Korobov from 2006, and for H2 with data from Pachutsky and Komasa. Note that in these papers, the number of basis functions needed to achieve this accuracy, and we're talking about really high accuracy in the nano-Hartree regime, was 3,000 and 4,200. You can see from the energy difference that with far less basis functions, with our approach, we get very close to these reference data. And note that the energy difference is given in micro-Hartree. So this works. It was one of the technical issues. And there are, of course, plenty of other issues. You need to make sure that the symmetry is properly preserved, for which there are different options, of course. First option is that you design the optimization in such a way that you only invoke basis functions that have the proper symmetry features, which might be cumbersome if you would like to have an implementation that is easy to apply to another system. Then you can have a partial wave expansion in such a way that you properly couple all the basis functions in such a way that the, for instance, total orbital or angular momentum fits to the state that you are interested in. That is also, of course, technically a challenge. And you can also think about making sure that you approach the variational limits so that you are not suffering at all from these issues. The way that we proceeded here is we used projection operators, as indicated on this slide, so that we have a projection onto the proper subspace with the proper symmetry labels of our basis functions. The projection, unfortunately, needs to be done numerically only in certain cases, which we published this year in PhysRef. Analytical projection is possible. Let me also show you that this implementation actually works. This is a calculation on the energy of H3+. The energy scale is somehow arbitrary because we shifted by a non-adiabatic energy estimate. The accurate data you can find in the paper reference below. But what I would like to point out here is that our numerical projection actually works very nicely. You see on the x-axis the number of basis function growing. You see two reference data points as given as lines here above for floating explicitly correlated Gaussians. With 50 basis functions, which were published earlier, and also for ECGs with the global vector representation. And you see they are all higher in energy. Then we look at floating ECGs in this work. This is a blue curve, and then switch on the projection, and you see that we gain in energy. So this also works nicely and allows us to produce very compact basis functions. So we have technically, we have a machinery that allows us to look at few particle systems very accurately. I should say the reason why we can only look at few particle systems is that because of the geminals, we cannot exploit the trick that leads to the Slater-Condon rules that is present in the case of orbitals, where many of the integrals simply vanish. This does not happen in our case. And so eventually we have actually set up all the permutations that guarantee Pauli anti-symmetry explicitly and evaluate all the integrals. But we can do that, and so we can look at few particle systems, and obviously this is a major difference to what Sharon has talked about. And so if you really would like to go for an accurate wave function theory of this kind, you must compromise in size, and severely, as you can see. But you can look at interesting problems. So as you can see on this slide, the question is atom or molecule. So what do I mean by this? Consider a three-particle system. So we have two particles which are A and A, they are like particles, and another particle B. A is of one charge and B is of the opposite charge. Typical example, as you can see here, is, for instance, H-, where you have 2 electrons and a proton, and H2 plus, 2 protons, 1 electron. This is exactly the same system, right? Still, when you look at this, as in chemistry, you would immediately say H- is an atom, H2 plus is a molecule. But when you look at the Hamiltonian, which is also shown on the slide, the Hamiltonian is in fact the same, apart from the mass ratio. So it's the mass ratio that in the end determines whether we want to call this a molecule or an atom. I can show this also on my next slide in more detail. But before I do that, I want to point out that our theory allows us to look at all these cases because we have no bias with respect to the properties of the particles, right? We have never assumed anywhere that nuclei must be much heavier than electrons. So we can play around with the mass ratio. And that's what we have done. So you can see on this slide on the right-hand side as a cut through a density distribution, the density distribution that we evaluate here for this density operator, it's given here. And on the left-hand side, you see a more three-dimensional kind of depiction of the same situation. I think it's instructive to look at the right figure, where you see that the mass ratio is changed on this axis here. And we can actually see how the case that we would call an atom gradually moves into the case that we then call a molecule. So we can basically extract molecular structure by looking and interpreting these density distributions. You can do that also for a more complicated system, like for H3+ here, where we study the ground state. This is a state picture taken from a paper by Oka, and we look at this blue 1,1 state, and you see on the right-hand side that we again computed our wave function. From the wave function, the density distribution is a proper density operator, and look at the cut. And what we see is a single maximum, which we interpret as representative for this typical triangular structure. Okay, now let's switch to the relativistic theory, because I told you in the very beginning that we intend to use an accurate wave function with no bias with respect to the particles that we want to describe in a more general framework, and then that is in this first quantized framework that is provided by Dirac's theory of the electron. So now we first consider a single electron. You see, this is a Dirac Hamiltonian for a single electron in external potential V, or in, with some potential V, where we have the kinetic relativistic kinetic energy in this typical form C alpha P. If you haven't seen this before, alpha is a 3-vector of 4x4 matrices. The 4x4 matrices are matrices which contain on the off-diagonal Pauli spin matrices. Right, and so you have for alpha x, you have the sigma x spin matrices, for alpha y, sigma y, and so forth. There's another parameter in the Dirac Hamiltonian, that's this beta. It's a 4x4 matrix which is diagonal, and on the diagonal there are 1, 1, -1, -1. This is called the standard representation, and the beta is in front of the rest energy. Okay, and because of this 4x4 matrix structure of the Hamiltonian, of course, the wave function has a vectorial structure. It has 4 components, and it's called the 4-spinner. The 4 components are typically called large and small. So there is a large 2-spinner and a small 2-spinner, and that is due to the fact that the Hamiltonian, as you can see from these alpha matrices, has a 2x2 superstructure. Now, the spectrum of this Hamiltonian is depicted here on the right, and compared to the one of Schrödinger's to the spectrum of the Schrödinger Hamiltonian. In blue, you see the positive continuum of the freely moving particles, whereas here, what is sketched here are the bound state, for instance, electronic bound states. But there's a peculiarity with the Dirac Hamiltonian that there are infinitely many negative energy states which are separated by twice the rest mass of each particle from the states that we are usually interested in. The problem here is, of course, that since we have these states in red here that go to -infinity, they pose a threat to all variational approaches that we intend to apply in chemistry. There is a qualitative argument which makes this point very well, and that goes back to Brown and Ravenhall, who made the following point. Consider that you have 2 electrons and they are not interacting, for instance, in a central field potential like one provided by a single atomic nucleus. And then you basically can directly write down the total energy as a sum of the individual energies of these non-interacting electrons, because for each electron we can solve the problem analytically. And so this combination of all possible solutions of the single electron, let me go back, these possible solutions were depicted here on the right-hand side, give now rise to energy component in the spectrum for the 2 electrons, and they are depicted here. For instance, you can have 2 electrons, of course, being in continuum states and moving freely around. And of course, then the combination gives you also a continuum state for the 2 electron states, right? So all combinations are possible. And there's one combination that is very crucial, and that is a combination of states where one electron is in a positive continuum state and another electron is in the other electron is in a negative continuum state. And since these states stretch to -infinity, you can, by combining them, produce a continuum of states that ranges from -infinity to +infinity for the 2 electrons that are non-interacting. Now, for these bound states that are also present for the 2 electrons, right, they are suddenly embedded in the continuum. And so they are unstable. Now we crank up the interaction of the 2 electrons, and the bound states are no longer stable, and you would see what is called continuum dissolution, where the electrons would eventually move into this part of the spectrum. And that basically means that our Hamiltonian has no ground states. And there's also the reason why in mathematical physics, you would be always forced to write the Hamiltonian with proper projection operators. And that's actually the formal solution to the problem. I will show that equation on the next slide. I should say that these problems have hardly been observed in quantum chemistry, especially not in any implementation of the orbital-based theory since the 1980s. And so it was Pesca and co-workers who, starting at around 2006, actually tried to find this problem by properly implementing a theory that could show these resonance effects, right? And so one of their papers was, for instance, called, I think, In Search of Pathologies or so. And so they were the first to really observe the phenomenon. In standard calculations, the algorithm makes sure that this doesn't happen. And so the way to make sure that it doesn't happen is to surround everything by projection operators, so that you make sure that you focus on the bound states that you're interested in. But that is typically not a feasible solution for an algorithm. Those solutions are a bit different. A key to these solutions is, however, something that is called kinetic balance in relativistic quantum chemistry. And it is easy to see in a one electron picture, so in an orbital picture. And you can see this here on the slide. The two equations here in the center, they are nothing else but the Dirac equation, written in what is called the split notation. So rather than having the matrix equation, I have now split it into two parts where I exploit this large and small substructure of the four spinor. Now I can use the lower equation to relate large and small component. And this relation is called kinetic balance. And you see, you can make an argument that the rest energy is much larger than the combination of the potential and the energy itself. So basically what kinetic balance says is that the small component is the large component after application of this operator, and P is the momentum operator containing the gradient, right? And so the point is, if you represent this Hamiltonian in some form in a basis set, you need to make sure that this relation can be fulfilled by the basis set. And that is one of the key features for actual calculations. I should also say that this kinetic balance inherently in one way or the other is present in any of the approximate relativistic schemes, be Douglas Kroll-Hess or this Barish-Sadley-Snyder's approach or the exact two components. So kinetic balance is key for stable, accurate calculations. But now let's consider germinals, because we have a theory that works with germinals. Now with germinals, we need to derive the kinetic balance condition, which is an issue and a severe problem. It's done here on this slide for the two-particle case. For the two-particle case, that can be done. Right? First of all, you see that the wave function is a special form of a direct product of the individual wave functions of the two electrons, where we exploited a special ordering of the terms, which in the end is key to derive the kinetic balance condition. This reordering of the terms leads to a Hamiltonian, which is given here in equation 12. And you see already here these sigma p products, which were also part of the kinetic balance condition. Now we can derive the kinetic balance condition for these two electrons, and you can see already from these equations that they are much more complicated than what you have seen in the orbital picture. Right? And that's actually a problem. So while we can handle these equations for two particles, going to 3 particles and 4 particles will be a problem. It might be possible to use some approximations here, but that has not been investigated yet. Let me show you that it actually works for 2 particles. So we are now using our germinal-based theory to look at a 2-particle problem, which is the hydrogen atom or hydrogen-like atoms, where we have 1 nucleus and 1 electron. Interestingly, there are analytical results for this case available. We see those in this column here. And as you can see by comparison, the results that we get from our calculation compare well with the analytical data. So the theory that we have implemented works. The crucial point is that it's extremely hard to generalize to more particles. And if you remember, we want to go after, for instance, the accurate calculation of the hydrogen molecule binding energy. So for that reason, we went back to orbitals, because for orbitals, kinetic balance is easier. So our geminal-based theory certainly has advantages and disadvantages. And the key disadvantages is the kinetic balance problem. So the orbital-based method wouldn't have that, because we know what needs to be done. But then we need to have an efficient way to get a very accurate wave function, because we no longer have this compact, explicitly correlated representation of the wave function. And what we did is we combined that with a DMRG-based approach, which is, if you never heard about DMRG before, it's nothing else but a CASI-SCF type approach. It allows you to optimize orbitals, and also especially to get the state interaction parameters. And state interaction parameters are accessible in a full CI manner. They are approximate, but basically you approximate a full CI wave function in the orbital space given. So we use our Hamiltonian in the paper that we published earlier this year. As you can see, this is our first attempt with this new theory, and naturally you start with a non-relativistic Hamiltonian. For sure, we want to extend this. We use it in a translationally invariant form. We need to implement everything now in the DMRG framework. What we do have is, rather than the geminals, we have orbital bases for the electrons and all the other particles. Of course, now we deal with fermions and bosons, and then we have anti-commutation relations for the creation and annihilation operators of the fermions, and the commutation relation for the bosonic creation and annihilation operators. The full Hamiltonian in second quantized form for the pre-Born-Oppenheimer calculation you see here below. It looks a bit intimidating, but in fact the structure is as for the second quantized electronic Hamiltonian. For instance, you have these typical 1 electron terms, but then you have 1 electron terms for the bosonic part. Then you have the interaction part for the fermions. You have an interaction part for the bosons, and you have a mixed part. So that can be done. The wave function that we set up looks like this. In the end, we have a CI type expansion, and where the DMRG allows us to target the CI coefficients. We do have the product of orbitals for each of the particles, and then the proper symmetrization or anti-symmetrization of these orbitals. And we basically continue to optimize all the parameters. In the meantime, we have also implemented other optimization techniques to compare with, where we don't have the non-linear optimization, in order to be more efficient and to compare with what we have here. One comment on DMRG. You see again here on top the CI type structure of our total wave function, and we have this state interaction parameters, which we resolve in DMRG as a sequence of matrices. And that is called a matrix product state. For this matrix product state, the operator needs to be written in a specific form, which is called a matrix product operator. And this is what we call a second generation DMRG program, which allows us to easily implement such specific changes to a Hamiltonian. And now the DMRG procedure itself optimizes these matrices M. And once you're done with the optimization, you know the CI coefficients. Just conceptually, so that you understand what's going on. So we have this nuclear electron all particle wave function on top, where we have basically many particle basis functions for the different sets of particles with coefficients in front of them. And those we optimize stochastically. Then, as you can see here, these many particle functions, they form then a set for the representation of protonic states, and we have a set for the representation of the electronic state, and we can recombine them now in a way that was not possible in the optimization step, and the recombination is then done at the DMRG level, so that we get an extension of our expansion, and hence have more variational freedom. And certainly you would expect the energy to go down. And in fact, that happens. You can see this here at the example of hydrogen, where the near wave function, so where we stochastically optimize the restricted representation of our wave function to get a very compact representation that is as compact as possible for our system, is then improved by this DMRG step, and you can see that the energy goes down. Point is that this is very efficient, much more efficient than what you have seen before when we use just explicitly correlated Gaussian functions. The ECG result is here given as this red line here. So we don't reach this, but it took us far less time to get these energies. And it's much more time consuming to get the ECG result. Moreover, the ECG result, because of the fact that we cannot exploit the Slater-Compton rules, the ECG would be limited to few particle systems, and whereas here we can go to much larger systems. Not large in a typical sense when you consider molecules, but BH3 would be a very large molecule with 12 quantum particles, and those we can treat here, as you can see. This brings me to my conclusions. So I have introduced you to our work on a molecular structure theory from an all-particle germinal-based quantum theory to be applied in a non-relativistic and relativistic context. We have used stochastic optimizations and later generalized those to have a wave function that is orbital-based for all the particles in the system, which we then combined with DMRG to increase the variational space and hence lower the energies. There are, of course, many things that we need to do. For instance, for NIAP DMRG, we need to work on the removal of rotational contributions. We can exploit schemes that are well established in electronic structure theory, where entanglement measures are used to get a reliable DMRG wave function and so forth. This work was only possible because of the dedicated efforts of my people in my group. Especially, I would like to mention Andrea Murlo, Alberto Bayardi, Robin Feldman, and Benjamin Simon. This work was done in collaboration with Edith Matjusz from Budapest, and it was actually started together with Jörg Hutter at the University of Zurich and Ulrich Müller-Herold from ETH. So I'm done with my presentation. I welcome any questions that you might have, and thank you very much for your kind attention.
Thank you very, very much, Markus. Very impressive. I'm always impressed with the width of the science you're doing, and I'm trying to catch up. But rumors has that I will have a chance now because you're going to head the department, so you will not have much time for science, right?
Let's see how that works out.
Yes. We have a few questions. So let me start with a question from Henrik Koch. And this was about the time where you showed the relativistic Hamiltonian. By the way, he says, Markus, great talk.
Thanks.
So my question is regarding the translational energy component in the wave function. Mm-hmm. As you only enforce the expectation value to be zero, there is still a non-zero variance. Said in other words, your wave function is not an eigenfunction of the translational kinetic operator. What implications might this have?
But that question does not refer to the relativistic version of the talk, right? The point well taken. I can add another problem from my side, which basically means that I avoid answering the question. That is, what at all is the removal of the center of mass motion in a relativistic theory? So when you look at the Schrödinger Hamiltonian, what we did is clear cut and might have issues, as you just mentioned. I currently don't worry about that because I face much severe problems when I think about what kind of energy do I actually need to remove from my relativistic Hamiltonian. Because, I mean, when you look at this Hamiltonian, right, say you consider the traditional way where you do a coordinate transformation that isolates a kinetic energy operator for the center of mass motion. How would you do that for the Dirac Hamiltonian? So yeah, see, it's interesting how quickly you get into very fundamental problems here.
Indeed.
So if you allow me to leave it.
Yeah, you could do use the Q&A. There's a possibility for you to type an answer and to save it for everybody to read.
Oh, well.
That makes me move on to the second question here. So this is from Barry Mant, and he says, Professor Reiher, have you applied your approach to mixed leptonic systems, for example, positronium hydride or antiprotonic helium?
Not yet. The simple reason is that we have spent most of the time fixing technical issues, and the technical issues require incredible capabilities on the side of the students. And so those 4 students that you have seen were very devoted to the topic. And it's at some point a PhD thesis must come to an end, and that is a natural break on our progress. So these things are on our list, but we had no time to look at them yet.
And if I may finish with a question of my own. So for the next session, we're going to have a presentation by somebody who has the title, We Have No Time for Science as Usual. I would like to paraphrase it and ask, we have no time for molecular theory based on orbitals. My sort of view here is that, for instance, if I have a first order excitation Hamiltonian, it's a summation over the particles. Whereas if I have second order quantization, I have a summation over all orbitals. And I wonder if the orbital-based theory, as we try to include correlation, it becomes more and more complex. We're getting expansions that has the size of more than the number of electrons in universe. Something fundamentally wrong must be associated with such a theory. What are your own opinion about us trying to push the envelope using molecular orbital theory and not sort of, yes?
Why not go for a real space representation and just integrate the multidimensional Schrödinger equation and see what we get? Is that what you're asking?
Well, yes.
So for instance, this has been tried also by people in applied mathematics already 15 years ago. I'm not aware that anybody found a more efficient way of doing things than what we do. So I think if you ask me, so I like to play around with this, but from a practical point of view, there is something to the Born-Oppenheimer approximation and the orbital picture, which makes it so much more efficient, at least on ordinary computers, that it's the right way to do.
I'll leave the question with that answer. You could discuss it for hours. So I would like to conclude this session with all of us paying our respect to the speakers, Hiroshi, Gemma, and Markus, for excellent presentations. We're now going to make a 1-hour intermission, and we're going to meet again at 1500 hours Central European Time, or 3 p.m. Central European Time, to listen to 3 presentations, one by Hirata, one by Alana Spurugusik, and one by Martin Koch. So see you in an hour from now about.